So let me start. The first speaker is Professor Mahesh Kakde. He will give the fifth lecture on the Brumer-Stark Conjecture. So please.
Thank you so much. Okay, so this is the last lecture, and this again, the third part of the proof is about Ribet's method. Okay, so we constructed this Cus form yesterday, and we proved a theorem about some homomorphism from Hecke algebra to a particular ring that we get using this Cus form. And today we are going to use that Cus form to construct some cohomology class that we need. Okay, let me remind you what this just a piece of notation from yesterday. But I also want to make a couple of remarks. So I had this group ring form, this Cus form that we constructed, and this was congruent to x times W1 psi 1 minus WK psi 1 modulo x times theta modulo x times this theta, right? And yeah, so and then using this we proved that there exists a homomorphism from Tm tilde to W. This is surjective such that R mod x theta, this is injective. So the structure map is injective. Phi of Tm is contained in the image of R. So R mod x theta hash. In fact, we know more and about what happens to the image of Hecke operators, TL and the diamond operators, but I'll not write that down. And then the last thing was, if U is this particular Hecke operator, UP minus psi P, yeah, this is in Tm tilde. So if for y in R, phi of u times y is 0 in W, then y is actually in this ideal generated by theta. Okay, so this last property is the one that we are going to use today. I'll try to keep this here, and hopefully I won't forget that I don't want to erase this. So I want to make one comment here. Usually in Ribet's method, Ribet-Wiles kind of stuff, you construct a Cus form congruent to some Eisenstein series modulo only p-adic L function. Okay, but here in this case you get an extra congruence. You get x times p-adic L function, and this x is relevant only when there are trivial zeros. Okay, so we are getting some kind of extra congruence when there are trivial zeros, and this phenomena is not kind of that was observed earlier as well. So for example, it explicitly is mentioned in paper of Hida T. Lewin on anticyclotomic main conjecture that there's an extra congruence. I think the way they state it is that the congruence ideal does not divide the p-adic L function. So it's strictly smaller in presence of trivial zeros. But I think this is, so far as I know, this is the first time you use this kind of extra congruence to do Ribet's method directly. Okay. Now recall that M bar was this was the set of all p ordinary cuspidal new forms F. So all such F of weight K and level dividing N times P plus, because there's this M bar, I have an extra condition, right, which was C1. You take the P stabilization, apply the Hecke operator T to it. This is congruent to phi bar of T modulo the maximal ideal of that that ring O we had, right? So phi bar was I mean, it's basically reduction of this. You can go modulo the maximal ideal here and get the residue field. But we defined this before doing that theorem, right? So this was some homomorphism from the Hecke algebra to a finite field K. Okay, I'm not going to recall that today. So anyway, this is a finite set, and to each such new form, there's a Galois representation attached. So this is due to Hida and earlier in some cases by Wiles. So F is in M bar, and there's a Galois representation attached to this. I'll call this into some finite extension of QP. So let me call that E, which satisfies various properties. So one is rho F is unramified outside the level times P. Okay. Then for all L which are away from the level, you can define characteristic polynomial of the Frobenius. So characteristic polynomial of Frobenius at L is x squared minus okay, so the Lth Fourier coefficient of F plus right, so psi L, no, this is not group ring. Okay, so this has Neben type as psi. Okay, so so this is psi L. Just in about 10 minutes or so, I'm going to put all this thing in group ring families. So okay, so this is the characteristic polynomial, and then the third property is kind of important, is that this is ordinary at all primes above P. So for P dividing P, rho of F restricted to GP is of the form so psi eta P inverse cyclotomic character 0 here, and then eta P, where eta P is some unramified character. So eta P is unramified character, and so I just have to tell you what it does at image of the uniformizer under reciprocity map, and this is just the pth Fourier coefficient of Fp, so stabilized thing. All right, so this is just some Galois representation that that's attached to this. Now here is a piece of notation. Okay, so the idea is that this thing looks like an extension of this by this, and so we are going to construct some extension out of this Galois representation. Okay, using this upper right hand entry, and so I should also remember to tell you where things go wrong when P is equal to 2. What's kind of the conceptual hurdle when P is equal to 2? Okay, so VPF, this is the eigenspace of rho F restricted to GP. This just simply means that the span of 1, 0. Okay, so very explicit thing. Now, what you want to do in Ribet's method, which Mazur calls Ribet's wrench, is kind of somehow fix a basis of the global thing, which is incompatible, not compatible with this local choice of vector that you have made, and that and if you do things that way, then this upper right hand corner will give you a cohomology class that's unramified. Okay, so that's the basic idea of Ribet's method. Okay, so let me. So the way to kind of formalize this is to note the following thing. So so there exists tau in GF such that tau restricts to complex conjugation. Tau restricts to complex conjugation in G. So when you restrict this automorphism of F bar to something, so remember we have this field extension H over F. So with Galois group G, so when you restrict it to H, you get the complex conjugation there because H is a CM field, so complex conjugation is well defined. Now usually this much is enough to just take any tau like this, but that's not enough for what we do. So this is the kind of the part why I say it's a lemma, such that for all F in this and for all P dividing T, the subspace VPF, is that the notation? Yeah, VPF is not stable under tau, is not stable under rho F tau. Okay. So kind of, yeah, one has to look at various cases, including what happens when F is a CM form and so on. I don't know if this M bar consists entirely of non-CM forms. So we do have to consider the possibility that F is CM, but anyway, you can prove all these things. Okay, so this is the tau that we'll use to fix a basis. Okay, so choose a basis for rho F such that rho F tau is lambda 1 F 0 0 lambda 2 F. Okay, and these lambda 1s and lambda 2s, so this lambda 1 will be congruent to 1 modulo the maximal ideal of a uniformizer of E, and then lambda 2F will be congruent to chi tau mod pi E. And so this is the place where kind of everything breaks down for P equal to 2, because chi I mean, even if chi of tau is -1, that's same as 1 modulo 2, and so these lambda, so you don't have distinct Hecke eigenvalues, and so you can't. There's no guarantee that you can actually diagonalize this matrix, and so that's the kind of point where it breaks down right at the beginning, and so for P equal to 2, it's not even clear how to form a cohomology class using Ribet's method. And in fact, this upper right hand entry is not enough, I think, to get all the cohomology classes one wants when P is equal to 2. So you have to do, you'll have to do something else. I think that's kind of it's not just a technical thing. I think it's kind of a real conceptual hurdle that one has to overcome. Oh, okay. Let's see. So Maser whiles don't do this? Or? Okay, yeah. Yeah, it's possible. Right. So over Q, of course, I mean, Clark does something much more. He proves ET and C as well in that situation. Yeah, at P equal to 2. And there again, it's kind of a real hard work. He does things very, very explicitly. And the fact that you have Euler systems, I think, is used very crucially in there. So the proof of main conjecture at P equal to 2 is somehow, whatever has been proved is weaker at P equal to 2 in Wiles's paper on the main conjecture. Okay, so now I'm going to put all these Galois representations together into a group ring family. So we can work uniformly, but the underlying thing is kind of very simple. Okay, these are all usual things that one attaches to the usual kind of modular form. There's no group ring kind of thing here. So this is the total ring of fractions of T, and this thing is just same as the total ring of fractions of this. So it's just a bunch of copies of E. So E you can take to be large enough, and then you can tensor your Hecke algebra with that, right? We had this choice of O in the previous lecture, so we can just take that O to be large enough so that even this works. So, so as I said last time, it's not just about values of characters of G. You may have to enlarge it further, and these are the kind of things for which you need to enlarge it further. Okay, so again, Hida and Weil tell you that you can attach Galois representations. Now this time, what it takes values in is GL2 of A. So you are just putting these Galois representations together. Again, let me rewrite those properties. So rho is unramified outside N and P for all L not dividing NP. The characteristic polynomial of prob L is x squared minus the TL Hecke operator, right? So I can talk about this thing now because the values are in K, which is the total ring of fractions of this. So I can take the image of T inside this, TL inside this, and that I just denote by TL again. And then psi L epsilon cyclotomic to the K minus 1 L. Right? So this is the, just putting all the things together, and as usual, kind of ordinarity. So rho restricted to GP is psi eta to the K minus 1 star 0. I guess it's eta inverse eta, right here. So there is a P here, P here. And what is the, this is again some unramified character. So I just need to tell you what it does on the image of uniformizer under reciprocity map. And this is the UP Hecke operator. Okay. So, all right. So that's what your Galois representation is. Now you have fixed a basis for each of these rho Fs, right? We fixed a basis for each of these rho Fs. So we get a basis for rho. So I'll just say this here. We have fixed a basis for rho using our element tau, right? And so I can now, so I've rigidified the situation. So I kind of can write this down as a matrix, an honest matrix like this. Okay, so for all sigma in GF. And now these are the explicit things that we are going to work with to construct our cohomology class. Okay. All right. So before going on to kind of get our cohomology class, let me write something down here, and which I hope I'll keep here and not erase by mistake. So what happens when your sigma is in GP? You actually get your representation is equivalent to something upper triangular, right? And so you have a change of basis matrix, which you will just, which I'll denote by M sub P. So MP, this is MP psi eta P inverse K minus 1 sigma, and then something here which I don't care about, give a name, so because that will not show. So what is this MP? This is just some change of basis matrix, A, P, BP, CP, and DP. Okay, this is in M, I mean, okay, GL2 of K. All right, and our choice of tau. So this is why the choice of tau is important. Choice of tau implies that AP and CP are non-zero divisors in K. K is just a product of fields, right? So saying something is non-zero divisor here simply means that its projection on each of this field is a non-zero divisor, and yeah, this is just by this using the tau in that lemma. So you can take that as an exercise if you like. Now, if you compare what happens to the so what happens to the upper left hand entry of both these matrices, what you would get is something like this. So B of sigma, so this is the expression that I want to keep here. Okay, so this is just some thing you can do here. So minus A sigma. Okay, so this is simply by, so this is for all sigma in GP, and you get this just by comparing the upper left hand entry of this product and that product, okay, and just manipulating it a little bit. All right, so that will be useful later on. But now let's go on to see how we get a cohomology class. Okay, so rho f is a representation. What does it mean for it to be representation, and what does it mean for the entries of rho f? So rho of sigma prime, this is simply rho of sigma prime, and this is A sigma prime, B sigma prime, C sigma prime, and D sigma prime. Okay, so this is, yeah, I should have done some other step before. A sigma prime, B sigma prime. Yeah, I don't even need to write all these things. Okay, so you just compare the upper right hand entry of this product with this, so you get B sigma prime. This thing is simply A sigma times B sigma prime plus D sigma prime times B sigma. Okay, so I'm going to use this in a short while. So So this is all kind of classical Ribet's lemma stuff. It's nothing really new that's happening here, and I'll tell you what are the kind of new parts. Anyway, so I'm going to use this in a while, but again, I'm going to do something else now. So trace of row of Frob L, this thing is simply this times Frob L plus psi of Frob L. This is just from what the characteristic polynomial looks like. Okay, so Chebotarev tells you that implies that trace of rho of sigma, which is of course a sigma plus d sigma, this thing is congruent to sigma plus psi of sigma modulo I. So I did not tell you what I was. I is simply the kernel of this map phi, right? Phi was this map from em tilde to W, and then I is I tilde intersected with Tm. So this is just the kernel of phi restricted to Tm. Okay, so you get this. Okay, maybe this should be clear that these A, B, C, Ds are entries in these are in K, right? So A, B, C, and D, they are a priori entries only in K. But now I'm going to show you that A and D are actually inside Tm. So trace is inside Tm, and in fact the trace is congruent to this thing modulo I. So I can talk about these congruences. Okay, so A plus D is already inside Tm, and I can talk about this congruence. And similarly, A of sigma tau plus D of sigma tau, this is congruent to cyclotomic to the k minus 1 sigma tau plus psi of sigma tau modulo I. So this is nothing mysterious. I'm just taking so instead of sigma, I'm taking sigma tau. So this is lambda 1. So lambda 1 is putting all the lambda 1 f's together. A sigma plus lambda 2 d sigma. This thing is congruent to a minus 1 sigma tau plus psi of sigma tau. What did I do? Mod I. Okay, sorry. So no, I chose it so that this is complex conjugation. So I actually get something like this. Okay, and now putting these two things together, you get that A sigma is congruent to this thing mod I, which actually you can say that this is congruent to this modulo I and some large power of P, because this thing will be congruent to 1 modulo some large power of P. So from now on, I'll be working with some large power of P, and this power of P depends on the weight that I'm working in. So eventually you have to take large enough weights so that the powers of P don't matter. And if I'm rushed for time at the end, I'll stop writing this P to the M. But everything you have to do P modulo P to the M, and then for some large enough M that power of P does not matter. Okay, so that's one thing. So the two things this equation and this equation implies that A actually lies inside T, and it's congruent to 1 modulo I and p to the m. And d sigma is congruent to psi of sigma modulo I. Yeah. Okay. So now taking this thing, so star gives that b sigma sigma prime is congruent to b sigma prime plus psi of sigma prime b sigma. So this is sigma prime modulo I and some large power of p.
May I ask a question?
Sure.
In the middle of that board, where did the lambdas come from and why did they disappear? When
The lambdas, okay, I erased, did I erase it? Yeah, so the lambdas were, so I had these lambda sub lambda 1f and lambda 2f. This was rho sub f restricted, no, rho sub f of tau. So I chose a basis so that I get this, right? And my rho is simply putting all these rho f's together. So that lambda 1 and lambda 2 are simply all these things put together.
Oh, parameterized by f. I
Yeah,
see.
yeah. Parameterized by f. So this is an element in the Hecke algebra. And yeah, so and then the other thing one uses to make them disappear is that lambda 1 is congruent to 1 modulo some maximal ideal of W, and then lambda 2 or maybe T. So let me write it as M. And then this was something like chi of tau mod M, and chi of tau is not 1. So you have two linear equations and you just solve them.
I could see if both lambda 1, oh, I see, and lambda 2. I'm just surprised because lambda 2, oh, I see the minus.
Yeah,
sign.
this is okay. This is like minus 1 more.
Minus 1, yeah.
And so when you add them together, you get 2 times. So this is where you see 2 is a problem, right?
Yep.
You can only
I
show
see
that
it
2
now.
times A is in the Hecke algebra and not A itself. Yeah, sorry, maybe I should have said at least, yeah, this much here. So 2 is a problem here because you wouldn't get such a congruence, and so you can't say anything here, and so you can't write down.
Equations would have said the same thing.
Sorry?
Because your equations would have said the same thing.
Yeah.
Thank you.
Yeah, the equations are fine except you can't. So now you can't divide by 2. So now you put K sigma to be psi of sigma inverse B sigma, and then using this, you see that kappa of sigma sigma prime is congruent to kappa of whatever the co-cycle relation should say, psi inverse of sigma kappa of sigma prime. Okay, again modulo this thing, which I'll stop writing. Okay. Yeah, again, all this is kind of classical Ribet stuff, some sense. Okay, so let me define a module now, which I'll call B. Remember that we are in case 1. Okay, so recall that we are always in what we called case 1 from yesterday. This was P and N are co-prime. This was the case. If P is not co-prime to N, some of the things that I'm going to say change slightly, but this is somehow the harder case anyway. In particular, this definition of B changes. So B is the T submodule of K. So Tm submodule of K generated by B sigmas for all sigma in GF. Okay, so that's my module B. And if I take, if I take B bar to be B modulo I times B, then kappa is a cocycle in H1 GF B mod IB. Okay, so B bar psi inverse. And this is kind of the classical Ribet stuff, right? This is the class that you would get in Ribet's method. And then you would want to show that this has nice local properties. Okay, except that this does not have the local properties you want. Remember, you wanted something which is unramified outside sigma prime and then at most tamely ramified at sigma prime. Sigma, of course, because we are in case one, is empty or just Archimedean places, so there's not much to show there. So this is not the right class in some sense. But anyway, we are going to use this class. We are just going to look at it in a different cohomology group. Okay, we are going to look at it in a quotient of that cohomology group. So let me keep this here. I just need that equation, but let's not confuse many things. I'll confuse myself. So all right. So what do I want to do? I don't want to take that kappa inside that. I want to take it in a quotient of this B bar. And what is the quotient that I take? So B prime is, okay, so okay, let me say this in words first before doing. So the problem is that this will not be unramified at places above P, right? Sigma prime does not contain any place above P. So I want kappa to be unramified at all places above P, and this class will not be. Okay, so what do? We do again something very stupid. You just kill all the ramification. Okay, so that's what I'm going to do. You just brutally kill everything. So this is again a Tm submodule of K generated by, this time you just take these inertia subgroups for all P in P. Okay, so again, as I said, we are in case one, so things are kind of slightly simplified notationally. Otherwise, you have to do different at ramified places and unramified places. But that's not the important thing. So this is inertia subgroup at P. Okay, so that's one thing. So let me actually, yeah, I should have been sort of, as I said, I'll not be very careful with my powers of P, but actually I should have kind of said this here. But I mean, I had already declared that I won't be careful. So, so instead of my B bar, I take what I call B sub P bar. This is B modulo the submodule generated by I times B, P to the M times B, and then this B prime. Okay, and I still get a cohomology class in this module, and I'll denote it again just by kappa. Okay, because I won't be using that kappa anymore. You know, I won't use kappa as a element in here, so I'll abuse the notation and just write that.
In the notation for B prime, you've written for all. So are you letting sigma run over the intersection of the inertia groups or the?
No, for yeah, maybe the order should be changed for all P in this and for all sigma in this. No, not the intersection, all. Yeah. No, that's the way I kill all the ramification. As I said, I want to brutally kill all the ramification. Okay, now what can go wrong if you do something like this? You could, our eventual thing is sort of, our eventual goal is to construct a large enough module. So, okay, what do we want? We want kappa to have certain local properties so that we get a surjective homomorphism from our nabla to this BP, and this BP bar, we want it to be large. Now, the thing that can go wrong by doing this stupid thing of killing all the ramification brutally is we may make it too small. So in the end, the kind of the thing, the thing where sort of something actual mathematics happens is to show that this is large enough. Okay, so that's the new part. That's the modification of Ribet's method that we do. All right, so good. Don't have much time. So, okay, here's the proposition about its local properties. So I'll quickly just see to this. So kappa as an element of H1 GF E sub P psi inverse is unramified outside sigma prime at most. So I'll just say tamely ramified at sigma prime, and then locally trivial at sigma, but sigma is empty, or sigma is just Archimedean places because of our assumption. Nevertheless, let me write it down because that's one of the conditions we had. So locally trivial at sigma. So we don't really need this in case 1. Okay. All right. So how do we show something like this? So here's the idea of the proof. Well, outside NP, this is unramified, right? So this is rho itself is unramified, and so of course kappa will be unramified, and sigma prime. This is all prime divisors of, because again we are in case 1. These are prime divisors of n, and so we have to show that at places in n we have at most tame ramification. But this just comes, and none of these places are above P. So wild inertia is sort of pro L, right? So wild inertia is pro L, where L is the residue characteristic of whatever prime you're considering. So again, I'll not dwell over that. It's just the topologies are incompatible, so you have at most tame ramification. And at P dividing P, we have killed ramification, right? So we have done this kind of stupid thing and killed all the ramification anyway. So there's not much to prove. So this thing is not hard, right? Now we have our cohomology class with right local properties. Of course, it may happen that we simply don't have enough elements in the module that we want. Okay, so hence we get whatever it was called, nabla H minus to this BP bar. Okay, so now our aim is to show that, so our goal now is to show that the fitting ideal of this BP bar is contained in theta. Okay, so that's our okay. So we, although we have killed the ramification, we haven't made the module too small. That's the part that's remaining now. And so we do some fitting ideal computation, and this is kind of the, yeah, this I think is the most interesting part of whatever we do up to now. We kind of just follow our nose and and reach to this point. Okay, so here's a lemma before we can go to fitting ideal computation. So this module B that I had, right? This can be generated by some non-zero divisors over R. So B can be generated over as an R module. Remember, T itself was an R module, right? So everything over R by finitely many non-zero divisors in K, and let's call them, K is the field of fractions of Tian. So let's call these things B1 up to Bn. Okay, so these are some non-zero divisors in K which generate B as an R module. So again, it's some kind of compactness argument, and then if you have zero divisors, you can change them by something to make them non-zero divisors without changing the span, etc. Okay. So not hard. All right, and then so these are the prime divisors over P. Okay, I just want to give them, I just want to number them. Okay, so here's a, yeah, so that's one piece of notation. Then the for all I between 1 and R, let sigma I be an element in G sub I that lifts, yeah, so I think I'm just kind of giving any details now, that lifts whatever the uniformizer is inside GPI ab. Okay, so these are the things I fix. Now I can, yeah, so again, CI, this is small ci, this thing is B sigma I times psi pi, yeah, psi pi epsilon cyclotomic to the k minus 1 sigma I. Okay, so this is just some, yeah, I take this B and then apply that to sigma I, and then multiply it by something. Okay, remember that Pi is unramified. All primes above P are unramified. Okay, all right. So just rearranging this. So this was, yeah. So just rearranging this, and then the AIs and CIs. So AI is A sub PI, and CI, this is capital CI, C sub PI. Sorry about that. This thing will be U sub PI minus psi of PI plus some element in I. Okay, this is an element of B. Okay, so this is the element of B that I take. So this is my shorthand for saying some element of I, and I don't want to give it a name. Okay, just there are too many symbols anyway to start with. So this is where I used the expression on that board. Okay, so maybe I'll say that if you want to verify this later. So this is using, so this is my, we'll start. All right, so so now I take a generating set for my VP bar. So take C1 up to CR, B1 up to Bn as generating a set for my B sub P bar. Now this might look very confusing because it is, I guess. I said that B1 up to Bn already generate B, right? So they will generate BP bar as well. So these things themselves, I mean, images of these things themselves will generate BP bar. But I include this because I want to show some relation. So, I want to show that some Hecke operator annihilates elements of fitting ideal. So this is what will give me the Hecke operator. This is what gives me the relations. And so these, I do include these kind of redundant generators as well. Yeah, I mean, it might seem very funny at the beginning, but I mean, it's kind of not. Okay, so this is the generating set. Now, what does an element of a fitting ideal look like? It is just some relation. So you take the matrix of kind of n plus r relations between these n plus r generators, and you take determinant of that. That will give you the an element of fitting ideal, right? So let me call that matrix M. So this is M. This is in n plus r by n plus r matrix over R, such that M C1 up to CR, B1 up to Bn is 0 in BP bar. Okay. So now it's kind of some explicit calculation to show that. So I write this as two block matrices. So W is Wij. This is in M n plus r by r, and then Z is some Zij. This is in some n plus r by n. Okay. Maybe I don't know if I get my rows and columns mixed up, but in any case, so for each for all i's, what you have is summation j going from 1 to r, Wij Cj, plus summation j going from 1 to n, Zij Bj is congruent to 0. So this is 0 in BP bar. Okay, but now I just rewrite these things, right? I just take what these things are in some explicit way that I know, right? Cij. So what is this? So this gives me summation j going from 1 to n, a j by capital Cj times Wij u pj minus psi of pj plus something in I that I really don't care about, because eventually I'm going to apply the map phi to this, and then summation j going from 1 to n, Zij. Now Bij, these are so something in p to the m r, and then Bj, this is 0 again in BP bar, right? So this will tell me that if I look at the following matrix, its determinant is 0. I'm almost done. Yeah, but I guess I can finish on time today. So if I take the following matrix, M prime, which is different from because of these modifications I have made. M prime is this, again, some kind of block matrix. So Aj by Cj, Wij u pi minus psi p pj. What the hell did I do? Yeah, sorry, my notes say something else, but I think this is it. Okay, so this is the W part, and in the Z part, I again have Z ij plus some element in I plus some element in p to the m r times b j, and this the determinant of this thing. So determinant of this thing is 0 in Vp bar. Okay, again, kind of a, but now you see that there are all these AJs in some columns and there's BJs, and they are all non-zero divisors. So this implies that, I mean, I can, yeah, this is all happening inside K, right? This is all happening. No, so, oh, no, sorry, what, yeah, what am I doing? No, this thing is actually happening in kind of B, not the bar. That's why I have all these I's. Yeah, sorry, that's what was confusing. So this is in K, right? This is all happening in K. So I can get rid of these things, and I can write Wij U Pj minus psi Pj plus I, and then Zij plus I plus p to the m r. This thing has determinant 0 in K. But now actually you see that all these elements are inside t to the m itself. So this thing, all this is happening inside t to the m. Yeah. And when you apply, so you apply phi to this, you could not apply phi here because this was not in t to the m. So now you can apply phi to this. And what you actually get is product UPI minus, okay, maybe I'll stick to this, psi Pj, phi of this thing times determinant of the original thing that you had with the Wij's and Zij's. This is 0 now inside W, okay, because you have applied phi to this thing. And we are basically done, because determinant of these are relations over R, right? Your M was inside R, so determinant of M is an element of R. So that M is an element of R. So that theorem there implies that determinant of M is contained in this, and so this implies that fitting ideal over R of BP bar is contained in theta hash. Okay, so putting all this together, finally what we get is that fitting ideal over R of nabla sigma prime sigma h minus this thing is contained in yeah, I hope this is right. Yeah, and then you as Samit pointed out, you use class number formula to get equality. So so this is, again, this part is kind of standard in Iwasawa theory now. Class number formula implies the equality. And so that does. So I'll stop here.
Are there any comments or questions? Can I ask you something?
Sure.
The matrix, the
Yeah.
entries of matrix, A sigma, B sigma, C sigma.
Huh.
You said, I think you mentioned some integrality about that.
Yeah. So,
Could you explain it again?
yeah. So, so a priori, they're all entries of K, but because of the way we choose our tau, what you can show is that A and D are entries of the Hecke algebra itself T. And actually, you can show more. You can show that B times C is an entry of T because the determinant is, and so on. So this is what is called GMA in the language of Belaitian ABA, I think. Generalized matrix algebra. So you have entries in the ring and then entries in some fractional ideal and such that the product is again in the ring. Yeah. So that's the integrality property. And so if you choose an arbitrary basis, you won't have anything like that. It's only because of the special choice of T we get a tau that we get something.
I see. Thank you. Any other questions?
P distinguished, yes. And so, yeah, and that fails at P equal to 2. So, so we can't do any of this. You need some new idea.
Any others?
Could you remind us what W is the codomain of phi?
So, I mean, the theorem said there exists a W R mod X theta algebra W which satisfies all these properties. Okay, and then very briefly I sketched what W would be. So if you want, I can do it again quickly. So so you take this you take this thing to be the Tm orbit of phi k psi, and then there is a map from Tm tilde to the endomorphisms of F. Okay, this is over R mod X theta, and W was the image of this. So W was image of this. I can write down more steps in between the two if you want. I can do that.
All right, thank you.
If no more questions. Okay, so let's thank the speakers for the series of wonderful lectures.
Thank you.